Sorry?
Let's go.
Okay, okay, great. Great, okay, thanks. Yeah, so in the... In, okay. Okay, so yeah, let me start with some sort of heuristics. Okay. The first one is actually a little bit differential geometry or symplectic geometry. So let's say you start with a symplectic manifold. So it's a symplectic form. Okay? And we assume pi 1 of m is trivial. Okay. Then, well, I can look at the free loop space. This is all the continuum maps from S to M. Okay. So here, this is S is just this circle, okay? A circle. And this is continuum. Now, because of this condition, I actually know so this pi 0 of Lm. So this is also trivial. Okay. So it's connected. Then what I do is I want to make this simply connected. So I pass to the universal cover of this space. Okay. So this is the universal cover. Inside of this, so this universal cover, a point inside of this is basically given by D and also this boundary. Okay. Modulo some equivalence relation. So basically this D is this disk. And then this boundary is just S1. So it's just really the boundary of this disk. Okay. So a point is represented by a disk and this boundary. So this boundary basically remembers which continuous map from S1 you have. Okay? And then this disk, you should think of this as a homotopy from S1 to the constant loop. Okay. Now, on this space, I can define a function. Okay? So this is mapped to R. Okay? So what I do is for each this disk and together with boundary, I mapped. Okay, this is mapped to the integral over D with this omega. So here this omega is a 2 form. It's a symplectic form, so I take the integral over this D. Okay. Then I get a well-defined function. So the reason I pass to universal cover is just to get a well-defined function. Okay. Yeah, so then you get this function, then Morse theory really tells you that whenever you have a manifold together with a function, you should look at the critical points and also the Morse index, etc. Okay, so then we'd also like to understand somehow a Morse theory. Of this, let me call this F. Of F. Okay. Now, of course, this universal cover of this free loop space is not a finite dimensional manifold, so you cannot use the ordinary Morse theory. And then, but there again, people have developed this infinite dimensional thing, but unfortunately, so this F is not a Morse function. It's not a Morse function, which means that so the critical manifolds, they do not have the required transversality for this infinite dimensional analysis to work. But somehow we still expect So we still expect that one can recover the homotopy type of, okay. I mean, when you have a finite dimensional manifold and you have a Morse function, you can hook up with the critical point and also flow lines. You can basically recover this manifold. But if f is not a Morse function on a manifold, you can somehow still recover the homotopy type. And here we expect a similar thing in this case. And this is basically a conjecture of Cohen, Jones, and Ziegel. Okay, so that's basically this conjecture. But somehow they actually formulate this. If M is the underlying manifold of a, let's say, final or maybe rationally connected varieties. Okay, so that's the idea of this conjecture. Okay? But somehow they also did some work so that you don't have to work with this infinite dimensional thing. You can just work with the projective variety. So let's say X is now a smooth projective variety and it's rationally connected over the complex numbers. Then you can consider this pointed scheme. Okay, so X is a point in this X, and this is the set of all the algebraic morphisms from P1 to X, so that it maps 0. Okay, so this is the algebraic scheme. And then this, here you have to add a plus or dagger here. So I will explain what this means. So given any such holomorphic map or algebraic map, you can look at the induced map on the topological space. So P1 is just S2. Okay. Then what this is that you just look at all the maps from S2 with the point. So this is all the continuous maps. Continuous maps. Okay. And then it's also the double loop space of X, just by definition.
So what does this plus sign mean?
Yeah, I have to explain this. Yeah. So, I mean, for each irreducible component, of course, you have a map, okay? You just think of this as a continuous map. Now, what is this plus sign? This plus sign is essentially, plus should be a homotopy group completion. Of a partial compactification. I mean, why do you need something like a homotopy group completion? It's because on this side, this space has almost like a group. Okay? Because if you have two spheres, okay, mapping to X, okay, they can glue them together, and you get a new. Then you have a new sphere. Yeah, this is sphere S2. So you can map the equator to a point. So you get something like this. And then if you have a map from this one, this is also a sphere. This is also a sphere. So if you have a map like this, if you have two maps, you can glue them together, and then you get a continuous map going this way. So that's why this is like an H space. Yeah.
It's up to homotopy.
Yes, right. So then you want this side to have the same structure. Okay. Okay. So then, okay. Okay. I haven't. So this is a homotopy equivalence. Homotopy equivalence. So after homotopy, this side should have a similar structure. And how do you, here, what you have is you need to somehow partially compactify this because you have to allow like a broken line. Yes, this is a conjecture. Conjecture is this is the homotopy equivalence. Okay. Okay. Then of course lots of work has been done. In fact, so work has been done even before they produce this, propose this conjecture. So the first work is done by Siegel. He considers the case when x is just p1, and they can compute both sides quite explicitly. And you see there is an homotopy equivalence. And later people have extended this to like all the projective homogeneous spaces and toric varieties, etc. So you do have this kind of isomorphism. Okay, but somehow, you know, all these works, they really rely on the geometry of X. It seems there's no way that you can, oh, maybe I should also, before that. So this conjecture, so it basically says that if you have this kind of thing, then you should have this. And conversely, if you know there's a homotopy equivalence, then there's a way to recover M. Okay? So you see, so this is, you don't see the function at all in this conjecture, but somehow, so it took some work of these three guys. They proved that this is exactly saying this. Okay. Yeah. And so, you know, all these works, all these previous works which verifies this conjecture, and it depends on the somehow a more or less concrete description of this side. Okay. And then you can compare these two. So I would like to somehow take a different approach. So I want to, you know, so the map is there. So I want to compute the homotopy groups on both sides and see if they are actually isomorphic. Okay? So what about the homotopy groups? Both sides. Okay. So I call this algebraic side, and this is the topological side, right? So of course, the answer on the topological side is easy. They're just pi I plus 2 of x. Okay. So this is easy, just by basic things in topology. And what is this pi I of this algebraic side? Well, you see, so it should give you some algebraic invariant, right? So you start with x and then rationally connected. So this is something, you know, purely algebraic, and you hook up with this almost like a H, this is an H space, and then you compute a homotopy group. That should give you some algebraic invariant. Okay? So then you would really like to understand what is this, and then there's a map here you want to understand, is this an isomorphism? Okay. Now, the only answer that I'm aware of is, so pi 0, this side, should be isomorphic to a1 of x, if this conjecture Okay. So this is the first evidence. Okay. So on this side, if you compute the pi 0, it's already a group. So it's already a group. And then it should be isomorphic to A1. This is a child group modulo 1 cycles modulo algebraic equivalence. But this uses some previous work of myself and my colleagues. Yeah. Then you can ask, so what is pi 1? Then, I mean, we don't have an explicit answer, but this is probably related to the Coneval filtration we talked about. This is probably. Okay. So you compute pi 1, this is probably the Coneval filtration. But I don't have a rigorous proof at this moment. So then you can continue, but the rest of them, I don't know. Okay. Then if you just look at this pi 0, so what is this I equals 0? So this pi 2 of x. So this is isomorphic to actually h2 of xz. Okay. So now if this conjecture holds, you should have an isomorphism. Okay? So now the corollary is that, so if this conjecture holds, then A1 of x is isomorphic to H2 of xc. Okay? So if I remind you, so in previous talks, we have seen that this is a very nice, this will have really nice consequences. Okay. So, but again, here you see that I like this way of thinking about this problem. So you start with some general philosophy, and you see, oh, you should have this isomorphism. And this is again, this is a conjecture of Mazal. Right. And so before, we just look at the examples and see, oh, we wish this could be true. But now this conjecture gives you an explanation. Okay? Just at least from this more theoretic point of view that this should be true. Okay? Yeah, so this is the first conjecture I want to talk about. And then, again, the second thing I want to talk about is a heuristic, again a heuristic. So this might be due to Manning, but I don't know. So let's look at a different. So let's say xd inside of Pn Q. Okay? This is a smooth hypersurface of degree d. Okay. So we want to look, H is, okay. So if X is in this XD of Q, then X can be represented by X0, Xn, where Xi, they're in integers and relatively prime. Okay. And I clear the denominators to make them integers. So then I define the hx, so the height, to be the max of all these xi's. So the absolute value. Okay.
Oh, so you don't take lower.
Yeah. I mean, if you take, you see, there's a reason I don't take logarithm. Okay, so now of course I would like to understand this. So fix n really large, okay? So I want to understand the number of points of x in xd of q, so that the height is at most n. Okay? And I want to understand this as a asymptotic formula. Asymptotic formula as n goes to infinity. Right, this is the number. I'll call this okay, just B and H R. Okay, so HX. Okay, let me call this MN. Okay, MN. So how do I understand this problem? Well, X is defined by f equals to 0. Right? So I think of this f as a function from z to the n plus 1 to z. Okay? So here you just plug in the number and you get a function on this. Okay? So then the zeros, well, so then it's x cubed. So z points, okay. So they are just the number inverse of 0. Okay? So it's the inverse image of 0.
Modulo.
Yeah, modulo some equivalence relation. Okay. Okay. Modulo. Okay. Now, if the height is at most n, and this has degree d, so you'll see that. So I take the sum. So then, if xi has the absolute value is at most n, okay, so then this f, the absolute value is at most n to the d times some constant c. Okay. I mean, it's a very rough estimate. It's just bounded by this thing. Okay. Now, so now here's a big assumption. So assume that as n is really large, so the values of f are equally distributed. Equally distributed. Okay. In other words, so within this range, there's an equal opportunity for each value. Okay. So then, how do you understand this set? Of course, so then you would expect that. So the number of this mn. Okay. This number. This is a constant times n to the n plus 1 minus d. Okay. Because here, when you bound the absolute value, here you have this many n to the n plus 1 choices of possible integers. And then the values, if they're equally distributed, then for each value you have equal opportunity. So then
Maybe modulus and logarithms, because you need to take quotient by this relation.
Yes. So this is again a very rough estimate. So this is somehow. I mean, so that you get, you think that so the rest is the major term. Okay, So the main term should be something like this. Okay, and of course this only makes sense if D is at most n, which is exactly the final range. Right? I mean, if D is n plus 1, or it may be greater or equal to n plus 1, this estimate certainly doesn't make any sense. Okay?
So it's maybe, I feel this it's called Manning conjecture, right?
Right, yes. Yes, so this estimate is exactly the Manning conjecture. And then later, so people actually figure out.
You should divide, so like the logarithm should be, it's up to logarithm. Yeah.
I mean, no, so the logarithm has to do with the Picard number, right? I mean here, okay, so if n is greater or equal to 4, okay, so it's Picard number 1.
Also,
Yeah, so you don't see the logarithm. Yes, you're right. So the general formulation, well, it involves some logarithm here, log n, maybe like rho, the Picard number minus 1, I think, right? Yeah. Okay, but anyway, so this is only a very rough heuristic, and you can find counterexamples to this count. So this tells you that it's not as simple as you would expect. Okay? So basically, this assumption is just too strong in general. But somehow, I mean, if we put these two heuristics together, you will see that they all have something very similar to each other. Because, so here you have to assume an equidistribution, okay? And there, you also have some kind of equidistribution, because if you look at the topology of this omega 2, so this omega 2 x, this is a map to x. Okay. So you look at it's a sphere mapping to x, and you just map it to the s, maybe the infinity. Okay. So now if so here I choose 0 and infinity. So 0 is always mapping to x. It's always mapped to x, and then you just take the infinity, the other point. So then there's this fibers homotopy. Right, so the fibers are homotopy equivalent, so that the topology is basically the same. Okay? And that conjecture is also saying that, if you think about this way, so that conjecture is somehow also saying that when you look at this algebraic map, after some operations, the topology also stays constant because it's the same as this one. Okay? So you always assume like an even distribution or equal distribution of something. Okay? And in fact, I think this is now well known. So if you assume that, if you look at this conjecture of Cohen-Jones and Siegel, look at this analog over finite field, that will give you a count of the number of morphisms from P1 to X. Okay? And that count is somehow exactly predicted by this type of argument, by Manning's conjecture. Maybe. Okay. So you see, so these two conjectures, when you look at this case over function fields, they are somehow saying the same thing in some sense. Okay. So that's why I want to bring these two together. Okay. And of course, they're really difficult problems, and I'm trying to understand them, not trying to actually prove them, but trying to understand them from different perspectives. Okay. So this Cohen-Jones, Siegel, they're really saying that the home P1 to X is somehow the same as home from S2 to X. Okay. And here is in the topological category, this is in the algebraic category. Now I want to understand this kind of phenomenon in a different category. So this is a DM with torsion coefficients. So this is Wolowski's the derived category of motives but with C mod n coefficients. Okay. This is DM. So the nice thing about this category is that it's triangulated category and it's a rigid category, rigid tensor category. So you can make sense of everything here. P1 has an object here. X gives an object here. S2 also gives an object here. So that's the important thing. So S2 is also an object here. And X, of course, then also you have this home. You also have internal home. And there is an internal home of any two objects. Maybe I take this. So you also have an internal home in this derived category. So what I can try to understand is the pi I of this home P1, 0. Okay. So this is also an object. This is an internal home. Okay. Is that isomorphic to pi I of internal home of S2? Do you have an isomorphism? I mean, inside of this, because we can make sense of this S2 and also other spheres, so it also makes sense to consider this pi I homotopy groups, okay, inside of this category. And again, so let's look at what this is and what this is. So now, this essentially, Wolowski tells you that this is isomorphic to Chow 1 of X of I plus 2. C mod n. Okay. This is the higher Chow group, or in other words, motivic cohomology on this side. On this side, this is, you can also compute this, and this turns out to be H I plus 2 of X. This is the Breuer-Moore homology. Okay. So then you see this. This is the question. Okay. When X is rationally connected and smooth projective. Okay. And if you believe that there's a generalization to this category, then you should believe that there's an isomorphism going this way. And again, if you take I equals 0, you recover that conjecture about Chow groups of one cycles. Okay. Now what else? So how is this related to everything we talked about? So again, this is due to the theory. Let's say actual P bar is smooth. So then you have a long exact sequence. Exact sequence. I mean, Chow 1 X I C mod n to h I plus 2 x C mod n, the Gravois homology, and then to Cattle homology, x, and then the next term is Chao 1. I mean, basically, Wolowski proved that this is isomorphic to H. So this,
what is on the right?
this one? Okay, I'm sorry. Is it I minus 1. Okay. So the I minus 1. Yes. I mean, so this is the Taritsky cohomology of this motivic complex. Okay. So Wolowski proved that. No, so Wolowski proved that. So this motivic Z mod n d minus 1. So this is isomorphic to tau less or equal to d minus 1, and then pi Z mod n, where pi is from the tau side to the Taritsky side. Okay. This is the motivic complex. Okay. And we, as we recall, so this is h d minus I of x, so R d pi lower star of Z mod n d minus 1. Okay, so then this is, well, because x is smooth, this is just h. Sorry, I minus 2. Let's see, I is kh2. Yeah, okay. Minus 2 of the R pi lower star. So it's just this one. Okay. So again, this is just follow from the long exact sequence of for this this triangle. Okay. So then you see, if you believe this conjecture, then this should be an isomorphism. Okay. So when x is so then this conjecture would imply that when x is smooth projective and rationally connected, then all this khi of x should be trivial for any I positive. Okay? Because you always have an isomorphism. And then, so somehow this Cattle homology is measuring the difference of the cycloclass map. Okay. But somehow we don't want to stop here. We can even have a more general version of this. So when x or b, so x and b, they are all smooth projective, okay, and a general fiber is rationally connected, so that is an isomorphism. I mean, if you take B to be spec K, then this is exactly what you get here. Okay, so now you get a more general version. Okay, for rationally connected fibrations. So this is the conjecture I'd like to talk about a little bit. Okay. So what is known about this? So over the complex numbers, okay, when dimension of x is at most 3, then this is true. Okay. So it's a combination of works of Bloch, Srinivas, Mazal. Then in general, this is just completely open. Okay. Now, this is one thing. The second, let's say over an algebraic closure of the finite field. Okay? Remember last time, we talked about this. So when you have x over b, okay? So b is a curve. B is a curve. Okay? Then a general fiber SRC. Okay? So now if this A1 of this is okay. Let's first assume they're over a finite field. Now if A1 of x bar, so now this is over the algebraic closure. Answer is the L is isomorphic to H2D, okay, of dimension D, H2D of x bar, CL. Okay. So if we have this isomorphism, then we know Hasse principle holds. Hasse principle modulo Brouwer-Manning abstraction. Okay. Holds. For generic fiber. And this is something we proved, right? So if this is true, then we know Hasse principle. Now if you think about this, so this is really just saying that, so if, so KH3 of, okay, let me look at this. So we have this long exact sequence. Let's look at when I is, here, this is also I plus 2. Anyway, so we have this, right? This is surjective, okay? And here H2 and I is 0, so it's just the usual Chow group with torsion coefficients. Okay? And then the next, this term is KH3. Okay. So we have a long exact sequence going this way. So as I explained, because of this decomposition of diagonal argument, so you want to understand whether this is an isomorphism. It suffices to mod L. You look at this map. So Z is L. You just need this. You just need to know if this is an isomorphism or not. Okay. Now you see that if KH2 and KH3 are 0, KH3 of x bar, KH2 of x bar. Okay. So this conjecture says that it should be the same as KH3 of B bar. Okay. And KH2 of X bar is isomorphic to KH2 of B bar. So this is part of that conjecture. Now, how do you compute the Kato homology of a curve? Well, if again you look at this sequence, this is one cycle. So for curves, that's just itself. Okay? So this is definitely an isomorphism. Okay? And there's no higher one cycles. Okay? So KH3 is always automatically 0, and so is KH2. So this is 0, and this is 0. Okay? Now this conjecture, if this is true, it will tell you that you have an isomorphism in this way. And then this is an isomorphism. So star. So yeah, so this conjecture would imply that this star is an isomorphism. Okay. Right. So this conjecture would actually imply this Hasse principle modulo Brouwer-Manning obstruction, the special case of Colliot-Linz conjecture. And similarly, the next term you see is somehow related, that's actually also related to H3. Anyway, so this conjecture would actually imply integral Tate conjecture. For one cycle. SRC varieties defined over, and also SRC in codimension 1. Okay. Yes. So that's why I think this conjecture is worth studying. Because of all this works, you know that as long as you can prove this for this fibration, then you prove this integral Tate conjecture. Okay. This is clear? So now, so last time we also talked about this thing. If you have integral Tate conjecture for one cycles, you'll see. So last time we also talked about the cycle class map of char 0 of x over some field K to H2D. Answer is and K is local. And there I said that if you know this integral Tate conjecture for one cycles for smooth projective varieties, you should expect this for the central fiber, and then this should be an injective. So somehow this conjecture modulo this all the ingredients of the modulo of this minimum model program, etc. Some subtleties. They should always imply that this is the cycle class. It's injective. Okay. Yeah. So this is how these things are related. Okay. And then, but this, you see, so they only need the first few Kato homologies. So this conjecture actually predicts a lot, a large range of isomorphisms. So what do they say? What are the implications of these things? It's not so clear. Okay, and I think that's a question you can worth thinking about. Okay. Okay, so this is the version over dm. Okay? But if you think about the original version of Cohen-Jones and Ziegel, so that's actually it's about homotopy types. But this conjecture for Kato homology, okay, so it's more about homological types. Okay, so it's related, but not exactly quite So what you want to do is, HK, so it's like a motivic homotopy. Category. This is by Vovolsky. So Morel Vovolsky. Again, here you have this internal home from P1 with a point and X with a point. Okay. And you also have this internal home of S2 with a point. Okay. So then you can ask, inside of this category, do you have something you can say, okay? But I think you cannot just work with this category. Somehow you need a profinite completion. I believe you need somehow an analytic completion. In other words, so you see this conjecture over dm, I'm not formulating the conjecture over the dm with integral coefficients. Rather, I'm only formulating this conjecture for dm with torsion coefficients. Okay? There you can have this kind of isomorphism. But I think the same problem appears here. You somehow have to analytically complete this. It takes some analytic completion of this space, and then you can ask whether you have an isomorphism or not. Okay. But again, on this problem, I really have nothing to say. I honestly have nothing to say. And this is an interesting question that people have not really thought about seriously. But again, I think part of the reason is probably because this is too difficult. It's very technical to do all the computations. Okay. But again, how are they related? How is this one related to the dm version? I mean, basically, in dm, so there's a factor from h to dm. Okay. So for each x, for each object, for each variety x inside of this, you just map it to x, okay, in the dm. But so the x in dm is, you should think of this as an infinite symmetric product. So here you have x, and somehow this one you should think of it as like infinite symmetric product of x. Okay, so the notation is still x. So you still have an object here, but this is morally the infinite symmetric product of x. And that's why when you compute somehow like homotopy groups inside of dm, what you get is not the homotopy group of x, but rather the homology or cohomology of x. Right? So that's why you compute this dom isomorphism tells you that if you compute homotopy groups of the infinite symmetric product, you get the homology. Okay, that's the idea. Now, so here, x actually maps to the second symmetric end, 3, okay, etc., until x infinity. This is the symmetric product. And again, this home, it commutes with this limit, okay, this limit. So you see that if you can formulate a version where you also allow some singularities here, then this dm version, in some sense, should be just a corollary of this thing. Okay? It should be just like you take infinite symmetric product, and then you take a limit. On both sides, everything commutes with this going to infinite symmetric product, and then you should get the version on dm. Okay? And then, I don't know, so I think also an interesting question is, to what extent the conjecture in dm can actually tell you something about the conjecture on hk. Because you see on dm, because of this work of Bloch, Srinivasan, and Voisin, we actually know something. Okay? So, so the homologies are slightly easier to compute than homotopy groups, right? So if you know something about this dm, then can you say something about the question on H? Okay? And that's something I would really like to understand, but somehow I don't know how to do this. Okay. So is this clear? Any questions? Okay. So these are all the conjectures I want to talk about.
So, sorry, I have the question. So, is it expected to be true only for smooth, some good varieties, or for all objects of categories?
You mean this thing?
Yes.
I think it should only one x is smooth projection. Okay, maybe not smooth, but x has to be rationally connected. Okay, and
for varieties, also for some pieces of varieties.
for what?
So it's not for all objects of.
No, that shouldn't be true. I think. Yeah, this there should be some geometry of varieties. I mean, well, but to be honest, I haven't thought about this general, to what extent can we extend this to the whole category. But I would guess that that shouldn't be the case. Okay? That should be the guess. Okay.
But maybe there is some fiber sequence.
Yeah. Yes. Of course. I mean, so both sides they should be stable under fiber sequences, and right. So if I have a fibration.
I mean that this map, from left side to right side.
Yeah.
If maybe we have a map and we can compute its fiber or co-fiber, maybe in stable category.
Yeah.
So and this fiber just vanishes when X is rationally connected to Y.
Right. Yes. Yeah. Yeah.
So people don't understand what is the abstraction for this map to be.
That's right. Yeah. That's a good point. Yeah. So. Okay. So if you're an expert, that might lead to something. I mean, unfortunately, personally, I'm not really familiar with this type of thing. So I try to learn it, but again, I mean, I spent the semester organizing seminars, but anyway, so I couldn't really say much about this. I can just understand a little bit of the formulation, but somehow to actually do some computation to show this sequence is or maybe the fiber sequence, or I don't know. That's beyond my capability at the moment, I think. Yes. Okay, so this is all I can say about the conjecture. I think at this point, this one is far beyond reach, I think. So the DM version is still very difficult, but somehow maybe K-series and other things can help you to say a little bit. Okay. I mean, just to say, so even to define this map, I think it requires a significant work. Okay. So basically, the most natural way to define this map is to construct a map in this category, a morphism in this category from S2 to P2 to P1. But that actually requires lots of work. And as far as I understand, so it probably follows from some work of others, okay? But already there, you have to take analytic completions, etc. So it's just to understand, to really rigorously formulate this question would actually require lots of work. Okay. But for DM version, it's much easier. Okay. Okay, so now I have explained the conjecture and some status of the conjecture. And also the consequences, if you know this. And then maybe I'll just leave with one question. Okay. It's very simple. So what if X is dominant? Or maybe even better, so or Pm of G. Okay? So it's Gx on Pm. It's unirational, or maybe just like a quotient by some group. Can you maybe take a resolution because we're working with smooth varieties? Can you prove this? That's trivial when A is positive and just C mod n when A is 0. Yes, with torsion coefficients. C mod n. Okay. Well, it turns out at the moment all I can say is when A is 0, 1, and 2, this is okay. For higher values, I don't know how to compute that. Okay. But here, this is X is Pm mod G, so just take the quotient. Okay. Take the quotient. So this, I mean, again, this is somehow related to this integral Hauch conjecture, or integral Tate conjecture. But somehow, for all the higher values, in particular, I would really like to understand how does the algebraic equivalence change under a finite quotient. But I have no idea how to do that at the moment. Okay.
So J is about to be finite also.
Yes, right, finite. I think it's probably okay if G is like a reductive algebraic group, but let's say finite just for safety. Okay, yeah. And again, what I'm trying to say is that, there's a bunch of difficult, but I think interesting questions. I mean, maybe I should emphasize the interesting part. There's this conjecture about Cadel homology gives you a whole range of questions you can study, and I don't think that has been studied very much. And again, I don't know if you can actually. There's probably some ways to understand these things. For example, for like homogeneous fibrations, etc. But somehow should involve lots of techniques I'm not familiar with. But anyway, I think I would really want to advertise this question about Cadel homology for rationally connected fibrations. Okay, and I think maybe I'll just stop here. Okay.
So, do you know any relation between like the TV version of Jones Siegel and like topological version?
Yeah, that's another interesting question. So, I mean, just by general philosophy, this motivic version should imply everything, right? So it should imply the point count and this topological version just by specializing to, or maybe just by mapping to this category of homotopy things. But somehow this motivic version, there's the catch. It's so you see on this motivic version, I just write like home from P1 to 0 to x. In this motivic version, I take the internal home. I didn't even take any like partial compactification or group completion. Okay. I'm just asking whether you have a homotopy equivalence to home of S2. Up to completion. So I'm not even taking any kind of a homotopy group completion on this side, because in this H, in this category of, in this motivic homotopy category, this one already has the homotopy group structure, H space structure, because in H, so you already have the P1 and P1. So you already have this map. So that's this nice, I guess this is one nice thing about this homotopy, motivic homotopy. You can somehow make sense of mapping the equator to a point in that category. Just doing this. Yeah, so you already have this map. So this side already has that structure. And then this would mean that it's not the, you also have this home scheme from P1 x, okay, with mark point. Okay. So it's not this one. So this is the scheme. So that should give you an object in this motivic homotopy category. But that's not this one. Okay. So then you should also try to understand the relationship of this one with this, and also how, when you pass to the topological category, what's the relationship with the homotopy group completion and the realization of this one. So there's a subtlety there. But again, I would guess that they should be the same. Okay, and if you know they are the same, then the motivic version of this should give you the conjecture of Cohen, Jones, and Siegel. Yeah.
And so what is known about, like in a complex case, about rational homotopy theorem, rational connected varieties? So like if we tensor a cube, everything.
Oh yeah, that's another good question. I don't know. So, that's a very good point. Yes, I forgot to say. I would expect that if you take QL here, it should be much easier to prove an isomorphism, just by something very similar to this motivic for this decomposition of diagonal. So you see, so all these questions about integral Hodge conjecture, integral Tate conjecture, so they're trivial when you consider QL coefficients. Yeah, so I would expect that there should be something similar here, but again, it's not immediately clear that that should be the case. But then again, for this QL rational homotopy types, I don't know much.
Okay, so thank you very much.